Okay, hello everybody. So we are another one of the larger groups. I kind of lost track, but I think we have about 76 team members involved in this group. So again, as Patrick said, I can only really give you kind of a sort of a taste of what we're doing in this 10 minutes. So this is not advancing. Where do I send it? Let's just do it with that. Okay, so the VPL research is focused on a single scientific question, which is how would we recognize whether an extrasolar planet can or does support life? So embedded in that question, recognize speaks to measurements and detectability, can support life is habitability, and does support life is whether or not we're seeing biosignatures or global modification of the planetary environment. So the VPL is divided into 5 major tasks. As originally formulated, the first one was Earth as an exoplanet, with the understanding that you're sitting on the only habitable planet we truly know about. We've since expanded that task into the solar system as an analog for planetary systems, and so we're now using whatever we can from our solar system colleagues to try and understand exoplanets. The Earth through time, task B, is one where we look at the Earth as a series of habitable states throughout its history and try to understand as much about those states that are constrained by geological and biological constraints as possible, as again, a sort of a more measurement constrained habitable planet through time. The habitable planet task is more of a modeling task, and it looks at the interaction of the star, planet, and planetary system and how those interactions actually affect whether or not a planet is more or less likely to be habitable. The living planet is where our biologists get into this full scale. That involves fieldwork, laboratory studies, and computer models looking at how what gases that life might produce, how those gases might in fact impact the planetary environment, and also looking at surface reflectance signatures and so on. So that's really sort of the biosignatures on a planetary scale task. And then the observer task, which is this rainbow that's running down the middle there, that one is where we take what we've learned from the previous 4 tasks and we run it through both instrument simulators and also retrieval algorithms to try and understand and learn what would actually be detectable about the environments that we have just modeled and discovered. So I'll give you a few highlights in some of these tasks and just show you some of the basic areas we're working in at the moment. And then I'll finish with some of our activities for this past year. So at VPL, we're always revisiting the habitable zone, trying to understand more about essentially what that is looking at the factors that in fact affect where the habitable zone would actually sit. Now, I think of the habitable zone as a really good first order place to look for a potentially habitable planet. It's sort of the first thing we'll put them in a bin, but we won't stop there. And so as we look at the habitable zone, we're trying to understand what factors are in both the planet and star interaction are actually going to affect where those things are. This one here is recent work done by Ravi Koparapu, who just left, but he's here looking at, again, updating our understanding of molecular line lists. This is where they're very, very important, and climate models and understanding three-dimensional models of synchronously rotating planets, and just showing how, as we put in more of the physics and update our models, our understanding of where the habitable zone might be oscillates around a bit. But we're still working on trying to pin down, the limits for the habitable zone. So that's one area, and that's just one example of that sort of work. The other thing we're doing is trying to do away with the habitable zone altogether. So the other thing we're doing is looking at something called a habitability index, trying to generate a different type of metric for target selection. And in this one, it's much more multi-dimensional. It's not just where the star is and the planet is as in the habitable zone, but looking at a bunch of different factors that may ultimately affect habitability, and really trying to get sort of an analog habitability, sort of a variation of probabilities of habitability for a given target based on the potential characteristics it could have if we can't measure them, or on the actual characteristics it does have if we can measure them. And so this is kind of an example, and this is work led by Rory Barnes, who is here, and he has some posters out there as well. But looking at sort of not just dumping a planet into the habitable zone and saying, okay, we have 40 of these in the habitable zone, but I can only observe one. We then look at the characteristics that are known about that planet and break them out into a probability distribution of how many of the potential states they could have, for example, in eccentricity and albedo, would in fact be habitable. So this paper was published this year and this past year for NExSS, and it's essentially the beginning of a framework that we hope will bring in more parameters to look at habitability as a more multidimensional thing. The other thing we're doing, this is work done by Russell Dietrich, who's also here. He's a grad student working with Rory, looking at how orbital dynamics can in fact impact climate and potentially habitability for the planet. And so he's looking here in orbital parameter space with the initial eccentricity for planets and the mutual inclination to other planets in the planetary system, and showing that there are some all places in the space are not equal, and in fact there are some places where a planet can end up where the amplitude of obliquity variations can be significantly higher. And so we're trying to understand, based on observables or potentially running history, how orbital dynamics would affect climate. Another example of the work we're doing, this kind of goes into task B, the Earth through time. Jada Arni is working on this, and Jada up here, she has just gotten an NPP to come to Goddard. And so we're looking forward to her doing that, and she is going to be doing work that will ultimately support the LUVOIR mission. And sorry, the mission concept. And so, my confidence there. So what she's working on is looking at the Archean Earth, which she calls the pale orange dot, and understanding how hydrocarbon haze that formed in the Archean, we have some geological evidence that such a thing existed, how that haze might have affected both surface temperature and the appearance of the planet. And because hydrocarbon haze is something that can form in a planet in a habitable zone, we've also looked at sort of Archean Earth analogs around other stars. And that's work in preparation at the moment. That I am the bottleneck. I still have to review the paper, but we're going to submit it really soon. And she's sort of found that there are planets which are forced by stellar spectra that make it more or less likely that haze will form. And of course, this is interesting from an observational perspective to know whether it's more or less likely that we're going to get clobbered by haze when we look at a particular planet. Other things we look at, Earth's disequilibrium biosignatures, and this is Josh Christensen-Tutton's work, and he's sitting up the back there, so he's here as well. He also has a poster on this. So people talk a lot about disequilibrium being a biosignature. Josh actually knuckled down and quantified the thing, and what he discovered was that the canonical, if you look at it as far as the Gibbs free energy amount and you quantify it that way, the canonical oxygen versus methane biosignature isn't actually the strongest disequilibrium state in our environment. It is in fact the simultaneous presence of nitrogen and oxygen with liquid water ocean. And all of those things could be gotten at via observations with large telescopes. Some of them are easier than others. Believe it or not, probably the ocean and the oxygen are the two easiest. Nitrogen will be very, very challenging. But again, we're looking into disequilibrium biosignatures and trying to learn more about those. We're also looking at oxygen as a biosignature. Oxygen has many advantages as a biosignature. It's with the photosynthetic biosphere because you're harnessing the energy from the principal energy source in the system. You have a chance to make this a global biosignature with a big impact detectable. It's evenly mixed throughout the atmosphere, so it gets up into the stratosphere where it can be seen by transmission spectroscopy. And it also has absorption bands in the region of the spectrum where we're planning to build our telescopes. So oxygen is certainly something we should go after, even though, of course, we can also look for more exotic biosignatures as well. So with the understanding that we will at least look for oxygen, we're trying to understand it as best as possible and whether or not it in fact has false positives. And so in the previous year, you see most of these papers in 2014, VPL came up with a whole slew of potential ways to generate large amounts of oxygen on a terrestrial planet in the habitable zone. And that was moderately depressing, but we then moved on to, okay, so let's say that happens, how do we actually discriminate these false positives, the abiotic generation of oxygen from true oxygen? And so we've been working on that this year, looking at things like potentially nitrogen detection, again, very challenging. We'd have to push the telescopes for that, but also looking for the presence of other gases like carbon monoxide and collisional pairs of oxygen to discriminate them. And so this is work that's being done by Eddie Schwiedemann, who's also graduating this year. And he's just recently published a paper looking at potentially detecting CO, where you would not normally see it in a photosynthetic biosphere, and also the presence of dimers from massive oxygen loss. So these are, the O4 dimers are O2 molecules, or collisional pairs they're called, that form. And the interesting thing that came out of this study was it turns out that the sign that you have a false positive biosignature is in fact more detectable than the false oxygen that's generated itself. And so that would give us a chance to maybe, say, observe with JWST, detect those things, and decide, maybe we don't want to spend a lot more time on this target. We also did this for direct imaging, and we have simulators for coronagraphs that help us sort of simulate things for W1st all the way through to LUVOIR class objects. We also do laboratory simulations, and this is Nikki Peronto's work, and she is here as well, so you can talk to her. I think this is super cool. She has kind of an enclosed environment where she can grow microbial mats under different atmospheric conditions, say Archean conditions. She has mass spectrometry, so she can look at what these organisms are putting out under those conditions. And she, a biologist, made it an artificial star. So this is a grid of LEDs that can be tuned up to match the spectrum of a star, forcing the microbial mat system. I think it's absolutely brilliant, and I'm super excited because it actually has the VPL logo on a piece of hardware, which doesn't happen in my group very often. So here's her, the black is her artificial star. I think we've got like an LED missing here, we'll have to fill in, but it's actually coincidentally right near the 0.94 micron water band, so we might just keep that. But this red observation is actual AD Leo, and the black is her fake star, forcing the microbial mat. So activities, we'll just finish up here very quickly. I talked about Eddie, I talked about Jada. Community input, we helped with the laboratory spectroscopy white paper. We have team members who have infiltrated Exoplag, the Louvois STDT, and the Habex STDT, so we're helping out with our expertise there. We were participants in organizing and also attending the upstairs-downstairs workshop. And I just want to finish with this biosignatures workshop. Come ask us more about it. Nancy Kiang and Nikki Peronto and Sean Domingo-Goldman are leading this activity. They're all here, so you can talk to them about that. But essentially, it's a collaboration between NExSS, NAI, and the Exopag committees in getting together a bunch of people for both pre-workshop activities to discuss the state of the science for astronomical biosignatures, and then to have a 3-day in-person workshop. That's by invitation only at this point, but for in-person, but it will be open to everybody remotely, so please attend if you can remotely, and we'll have a whole heap of post-workshop activities as well. So I'm going to stop there, but if you need more information about that workshop, please come and talk to either me or one of those 3 people to learn more about it.
Questions for me?
Hi, Vikki. This is, what you've shown us is almost like a whole research coordination network in and of itself, right? I mean, it is, it's a very big team. You see that some of the presentations that we've heard today are like this, right? They're really big teams that are very integrated and have all of these different pieces, different activities that kind of feed into one overarching objective.
Mm-hmm.
And that's what NExSS is supposed to be, kind of on a big scale as well, right? So I'm wondering, as I'm listening to you, given the NExSS paradigm, like, what can we do to further this? Do you see any potential for maybe kind of activity groups that we could seed within the broader community, maybe like working groups doing something very specific, very research-oriented? Do you see the need for anything like that based on your experience?
It depends. There's multiple ways of going at this. So one thing we've learned. So VPL's been going for 15 years now. So we have quite a bit of experience in, or at least I have quite a bit of experience trying to herd cats and get people to work together. The killer app is the scientific question you want to address, and so it's really, really important to define a question that everybody can get on board with. And once you have the buy-in for that, the rest of it kind of falls out because there'll be enough interest to go into that. So, I mean, working groups would be one way to get at it, but I mean, we've kind of leapt over that in a sense and gone straight to the workshop idea where we said, okay, here's our overarching questions, and I didn't put them up there, but we have, a set of 3 things that we really want to do with this workshop. And so you can set that up. So there are multiple ways of going at this. We on VPL do not have science working groups within our own sense, but we do have questions that we've identified and tasks that we want to work on. So I think there's multiple ways of going at this, and I think we, the community, need to decide how we want to get into this. But I can tell you one thing about VPL is it started with 17 people. And so it has grown enormously in the last 15 years. And part of that is because, the questions that we put forward were attractive to others, and we were able to bring people in from the outside to get more involved. And then in the next proposal round, they became bona fide card-carrying members. So, yeah. So I'm happy to talk with people about trying to herd cats in that way.
Since there's nobody else standing at the mic, I just carry this thought a little bit further. We just finished our first year, and now we're thinking about what to do for the second year coming up, how we're going to make a difference. I'm wondering about workshops, I'm wondering about working groups, I'm wondering how we can create activities. I don't want to create a lot of extra work for people. I know we're all doing a lot of committee activities already. A lot of it is unpaid, unfunded, and we're doing just out of the goodness of our heart. But if we can think of things, of ways to catalyze the community and enhance our own research, it's kind of good for everybody, right? Mm-hmm. An example, I got a phone call from somebody in the community who's not affiliated with NExSS asking, do you guys have a working group that is putting together a database of all the star properties of the nearby stars that might be of interest to LUVOIR and HAB-X in the future? That's really something that needs to get done, right? Everybody's shaking their heads. We all know it needs to get done. So maybe that's something that NExSS could help to catalyze. I don't know. Mm-hmm. But anyway, I just wanted to end by saying I'm going to put a stack of Post-it notes here. If you have any ideas about kind of working groups or things, ways that we can see the community to catalyze research, please write it down on a Post-it and just stick it to this column. We're going to wrap up at the end of the 2 days, going back to that list. So if you think of anything, it could be a working group, it could be another workshop, it could be an EPO activity, whatever. Just write it down and put it up on this column. Okay?
Can I add too? I mean, we've been effective. Also, Jonathan Fortney's group leading that white paper on laboratory spectroscopy. So I mean, white papers where you can bring in other community members might also be a good way to go. Yeah, the specific deliverables, I think, are what impresses people the most.
Yeah, and I really appreciate your point, Vikki, that it has to be a very specific science question that we're all interested in attacking. Right?
Mm-hmm. Yeah. And as broad as possible to get as many people under. Yeah. Of course, the inevitable Dave.
Specific science question.
Sure.
I thought your point was really interesting that the biggest disequilibrium is actually the nitrogen and oxygen mix over water. But there's a sense in which methane and oxygen is still a lot more surprising to see, because you have almost zero kinetic barrier, whereas with the nitrogen, because it's so hard to break triple bonds, there's a huge kinetic barrier. Now, obviously, some bacteria have figured out how to do it, but how do we, not looking at a strictly Gibbs free energy equilibrium standpoint, but including kinetic barriers and such, how do we incorporate that into our assessment of biosignature?
So I think, and I'll let Josh pipe up if he wants to, because he's really the expert on this, but I think it's not so much breaking the nitrogen in the atmosphere per se, but this is the solubility of nitrogen, the formation of nitrate that would normally come out. So you can see on the bottom here, I've highlighted the fact that the nitrate is actually out of equilibrium as well. But the interesting thing about this is it's oxygen and nitrogen in the presence of water, and ironically the ocean detecting a glint might be one of our easier measurements in photometry, so that's not too hideous. Nitrogen is very difficult. There is a collisional pair at 4.1 to 4.2 microns, but the current telescope architectures we're talking about will not go out there, so that's going to be very challenging. But I will let Josh pipe up since he is the expert on this work.
Probably done it, just a couple of comments. So you're right in that the oxygen methane disequilibrium is particularly interesting because of this kinetically you wouldn't expect it to happen. And so something I'm working on is trying to formulate a better metric of disequilibrium that includes the kinetics. And if people have ideas on that, I'd love to talk to them. But on this nitrogen, oxygen, water disequilibrium, this is still something that kinetically you wouldn't expect in the absence of life, because eventually, like lightning will convert that nitrogen into nitrate. So